NASA says its Voyager 1 probe, the most distant human-made object in the universe.
In 2018, NASA's Voyager 2 spacecraft crossed the boundary.
Launched in 1977, NASA's Voyager missions have traveled farther than anything humanity has ever sent into space, venturing beyond Jupiter and Saturn into uncharted territory. Voyager 1 and 2 have crossed the solar system's boundaries, revealing cosmic phenomena that have transformed our understanding of the universe. But what did they discover at the very edge of the solar system, beyond the reach of our sun? Join us as we dive into the shocking revelations that changed everything we thought we knew about space. But before we dive into the incredible discoveries made by the Voyager spacecraft, it's important to understand the missions themselves first. What is Voyager? The Voyager missions, Voyager 1 and 2, were designed by NASA to explore the outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, and their moons. These missions were launched in 1977 during a rare alignment of the outer planets that occurs once every 175 years, making it an ideal moment for a grand tour of the gas giants. This alignment allowed the spacecraft to use the gravitational pull of each planet to slingshot to the next, significantly reducing fuel requirements and travel time. Voyager 1 and 2 were both equipped with a suite of advanced scientific instruments designed to gather as much data as possible. These instruments were capable of measuring everything from the planet's magnetic fields to their atmospheres, radiation belts, and moons. Each spacecraft carried a pair of high-resolution cameras, along with spectrometers, magnetometers, and plasma detectors. The data gathered from these instruments would provide humanity's first close-up look at these distant planets and their complex systems. The goal of the mission was not only to study the planets themselves, but also to explore the unknown regions beyond. Although the two spacecraft were nearly identical, their paths were not the same. Voyager 1, with its faster trajectory, overtook Voyager 2 and headed straight for the edge of the solar system. It was the first to reach the outermost boundary, and in 2012, crossed into interstellar space, making it the first human-made object to leave the solar system. Voyager 2, on the other hand, followed a longer and more deliberate path, making its way to Uranus and Neptune, before embarking on the same journey toward the edge of the solar system. While Voyager 1 ventured into the unknown more quickly, Voyager 2 made its own unique contributions by visiting all four gas giants. These twin spacecrafts have sent back a treasure trove of data that has reshaped our understanding of the solar system. From the enigmatic atmospheres of Jupiter and Saturn to the surprising features of Uranus and Neptune, the Voyagers have revealed a universe much more complex and diverse than we ever imagined. As the spacecraft continue their journeys even further into the great unknown, their discoveries continue to provide us with invaluable insights into our place in the cosmos. Now that you have a glimpse into the Voyager missions, are you ready to discover what these spacecrafts uncovered at the edge of the solar system? The edge of the solar system. What did Voyager detect? The Voyager missions are among the most significant milestones in humanity's exploration of space. Their discoveries have expanded our knowledge of the universe in ways that were once thought to be the stuff of science fiction. Voyager 1, which launched in 1977, embarked on a journey to study the outer planets, but what it ultimately achieved was even more monumental than initially anticipated. It crossed the heliopause, entering interstellar space in 2012. The heliopause represents the outermost boundary of the solar system, where the sun's solar wind, charged particles continuously released by the sun, finally fades away and interacts with the interstellar medium, a vast sea of gas and dust that exists between the stars. Prior to this discovery, no spacecraft had ventured beyond this region, making Voyager 1's crossing a historic and unprecedented event. It marked the spacecraft's entry into a realm where no human-made object had gone before, and the data it returned began to radically change our understanding of space. At the moment Voyager 1 crossed into interstellar space, it encountered dramatic changes in its environment. The solar wind, which had been flowing consistently throughout the spacecraft's entire journey, ceased abruptly. The solar wind had been a dominant force, creating a protective bubble around the solar system, known as the heliosphere. This bubble shields us from the cosmic rays and other harmful radiation that permeate interstellar space. But as Voyager 1 crossed the boundary of the heliopause, the solar wind's particles ceased, and the spacecraft began to measure a vastly different environment. One of the key discoveries was that of cosmic rays. These high-energy particles, primarily protons and atomic nuclei, had been flowing through the solar system at relatively low levels due to the protection offered by the solar wind. However, as Voyager 1 crossed into interstellar space, the cosmic ray intensity increased dramatically. Scientists were now able to measure the strength and type of cosmic rays present outside the solar system. This marked the beginning of a new era in our understanding of cosmic radiation. For the first time, we were able to directly measure the particles that permeate the interstellar medium, which is a key component of space's natural environment. Furthermore, Voyager 1 also began detecting changes in the magnetic field. In the heliosphere, the Sun's magnetic field dominates and creates a relatively predictable environment. However, once Voyager crossed the heliopause, it encountered a much more complex and chaotic magnetic field. The interstellar magnetic field, shaped by the influence of many stars across the galaxy, was far more turbulent than what had been expected. The magnetic field in this region was highly variable and fluctuated in intensity, and it exhibited irregularities that provided valuable insights into the dynamics of the galaxy's magnetic environment. This revelation forced scientists to reconsider their models of how the Sun's magnetic field interacts with the surrounding galactic environment, leading to more complex theories about the interactions between stellar winds and the interstellar medium. The data collected by Voyager 1 also included the first direct measurements of the interstellar medium itself. This region, between the stars, is made up of sparse gas and dust. Prior to Voyager's crossing of the heliopause, scientists could only speculate about the properties of this region. The data returned by the spacecraft confirmed that the interstellar medium was far more dynamic than previously believed. It revealed a medium that is not only composed of gas, but also exhibits fluctuating pressures, temperatures, and magnetic fields. The interstellar medium is composed of hydrogen, helium, and trace amounts of heavier elements. It is an essential component of the universe, playing a crucial role in star formation and the evolution of galaxies. In addition to providing groundbreaking data on cosmic rays, magnetic fields, and the interstellar medium, Voyager 1 also made some additional discoveries about space itself. The spacecraft encountered new types of particles, such as those from the galactic cosmic ray background, and it measured the overall density of the interstellar environment. The measurements of these particles helped to develop a clearer understanding of the physical conditions in interstellar space. Scientists have been able to track how these particles interact with the spacecraft and the solar wind, offering deeper insight into the fundamental processes governing space on a galactic scale. Another unexpected discovery was the interaction of Voyager 1 with the plasma wave in interstellar space. As the spacecraft moved further into the interstellar medium, it began to pick up the faint echoes of radio waves from plasma, which is an electrically charged medium made up of free electrons and ions. These signals were previously unknown to scientists, providing a rare glimpse into how the plasma environment behaves outside the heliosphere. Voyager 1's plasma wave instrument detected oscillations in the plasma density, providing clues about how matter and energy are distributed across interstellar space. In addition to these scientific revelations, the crossing of the heliopause also symbolized the beginning of a new phase in the Voyager mission. Voyager 1, after more than 35 years of operation, had entered an unknown frontier, becoming the first human-made object to leave the familiar domain of our Sun and venture into the vast expanse of interstellar space. This milestone also meant that Voyager 1 would continue to send back data that could provide answers to questions we never even knew to ask, offering a wealth of new data that would fuel scientific research for decades to come. This transition from the solar system's influence into the interstellar medium has provided a wealth of knowledge. The shift from solar wind to cosmic rays and the dramatic changes in magnetic fields and particle densities have illuminated how our Sun interacts with the greater universe. The spacecraft continues to provide invaluable data about the boundary between the solar system and the broader universe, acting as humanity's scout into the unknown expanse of interstellar space. While Voyager 1's discoveries at the edge of the solar system are groundbreaking, what did it uncover on its way there? And what about Voyager 2? What incredible findings did it make on its own journey? Keep watching as we dive into the amazing discoveries both spacecraft made long before reaching the solar system's edge. The gas giants Jupiter and Saturn. Before Voyager 1 made its historic journey into interstellar space, Both Voyager 1 and Voyager 2 made groundbreaking discoveries as they ventured toward and past the gas giants, Jupiter and Saturn. These missions provided humanity with its first in-depth look at the largest planets in our solar system, revealing features and phenomena that were previously unknown. Voyager 1's first major encounter was with Jupiter, which it visited in 1979. Prior to Voyager's flyby, Jupiter was a distant and mysterious planet, observed only through telescopes from Earth. However, the data transmitted back by Voyager 1 painted a far more complex and active portrait of the gas giant than anyone had anticipated. One of the first shocking discoveries was the planet's faint ring system. While Saturn's rings had long been known and admired, Jupiter's ring system had never been detected before. Voyager 1's images revealed a thin, delicate ring of particles made mostly of dust-sized particles. This unexpected discovery added a new layer of complexity to our understanding of planetary ring systems and highlighted the importance of space exploration to uncover hidden wonders. In addition to the rings, Voyager 1 provided remarkable insights into Jupiter's moons, which were far more varied and intriguing than scientists had imagined. One of the most significant revelations was the active volcanic activity on Io, one of Jupiter's largest moons. For the first time, Voyager 1 captured images of volcanoes erupting on Io, releasing plumes of sulfur and other volcanic material. This discovery shattered previous assumptions about volcanic activity in our solar system and identified Io as one of the most geologically active bodies known to science. Another major discovery came from Europa, another of Jupiter's moons, which was shown to have a smooth, icy surface. Voyager 1's data hinted at the possibility that beneath this icy shell might lie a liquid ocean. The idea that a subsurface ocean could exist on Europa opened up tantalizing possibilities for the potential of extraterrestrial life. Could the conditions on Europa support life forms? This discovery sparked a flurry of research, leading to future missions such as NASA's Europa Clipper, which will further investigate the possibility of a hidden ocean and the prospects for life beneath Europa's icy crust. Voyager 1 also passed close to the massive moon Ganymede, the largest moon in the solar system, and provided the first detailed images of its surface, revealing an ancient ice-covered terrain marked by craters and ridges. Meanwhile, another one of Jupiter's moons, Callisto, presented a more geologically inactive world with a heavily cratered surface, offering clues about the early history of the solar system. After its flyby of Jupiter, Voyager 1 continued on its trajectory towards Saturn, arriving in 1980. By this point, the spacecraft had already proven its capabilities, and its observations of Saturn's rings would be equally groundbreaking.
The spaceship left the solar system in 2012 and is currently more than 15 billion miles from Earth.
Saturn's rings, the most prominent and well-known in the solar system, had been observed from Earth for centuries. However, Voyager 1's close-up images showed them in far greater detail and revealed intricacies and structures that had never been seen before. Voyager 1 captured stunning images of Saturn's rings, identifying new ring segments and narrow gaps, including the previously unknown G-ring. One of the most exciting discoveries in Saturn's system came from Titan, Saturn's largest moon. Titan had long been a source of fascination due to its thick, nitrogen-rich atmosphere, but its surface had remained hidden by a thick layer of clouds. Voyager 1's flyby of Titan provided the first clues about the moon's surface, showing a hazy orange atmosphere composed mainly of nitrogen, with traces of methane. Titan's atmosphere is incredibly dense compared to other moons and planets, making it an object of great interest for scientists studying planetary atmospheres. The spacecraft's instruments were able to detect methane clouds in Titan's atmosphere and hint at the possibility of liquid methane lakes on its surface, which would suggest an active, dynamic environment. This discovery provided a new way to think about the potential for life beyond Earth, as Titan's organic chemistry and environmental conditions present an intriguing parallel to the prebiotic conditions that may have existed on early Earth. The flybys of Jupiter and Saturn, therefore, provided a treasure trove of data that not only revolutionized our understanding of the solar system's gas giants, but also ignited scientific curiosity about moons that could harbor the potential for life. Voyager's discoveries about these distant worlds opened up new frontiers in planetary science and laid the groundwork for future missions to explore these fascinating objects in greater detail. But Voyager's exploration didn't stop with Jupiter and Saturn. While Voyager 2 continued its journey toward Uranus and Neptune, Voyager 1's discoveries would serve as the springboard for even more groundbreaking revelations about our solar system's outer planets. The ice giants, Uranus and Neptune. While Voyager 1 ventured towards the outer limits of the solar system, Voyager 2 embarked on its own historic journey toward the ice giants, Uranus and Neptune, planets that had never been visited before by a spacecraft. Voyager 2's flybys in the 1980s provided humanity's first close-up images of these distant, mysterious planets, revealing worlds that were vastly different from the gas giants. Voyager 2 arrived at Uranus in 1986, and the data collected during this flyby changed scientists' understanding of the planet and its system. Uranus, which was unique for its tilted axis, about 98 degrees, was found to rotate on its side, unlike any other planet in the solar system. This tilted rotation indicated that Uranus may have suffered a massive collision in its early history, knocking it into its present orientation. Voyager 2 also discovered that Uranus has a faint ring system, though much less prominent than Saturn's. The spacecraft identified several dark rings, revealing that Uranus had more in common with Saturn and Jupiter than previously thought. The most striking revelation came from the planet's magnetic field. Unlike the magnetic fields of other planets, which are aligned with their rotational axes, Uranus's magnetic field is tilted at an unusual angle and is offset from the planet's center. This peculiar magnetic field structure suggested that Uranus's interior is far more complex than scientists had realized, with a mixture of elements that had yet to be fully understood. In 1989, Voyager 2 flew by Neptune, the last of the major planets to be visited by a spacecraft. Neptune, a world of intense winds and dark storm systems, presented a stark contrast to the more placid atmospheres of the gas giants. The spacecraft provided the first close-up images of Neptune's Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. This discovery confirmed that Neptune's atmosphere is not only turbulent, but also contains large-scale weather systems. Voyager 2 also uncovered the presence of fast-moving winds on Neptune, some reaching speeds of up to 1,500 miles per hour, making it one of the most extreme environments in the solar system. Perhaps the most fascinating find came from Triton, Neptune's largest moon. Voyager 2's instruments detected signs of cryovolcanism, or ice volcanoes, erupting from Triton's surface. These cryovolcanoes expelled nitrogen, methane, and water ice, suggesting that Triton, like Europa, may have subsurface oceans of liquid water beneath its icy crust. This discovery opened up new possibilities for understanding the potential for life in the outer solar system. Voyager 2's observations of these ice giants provided a wealth of data about the planets that would reshape our understanding of distant worlds. Uranus and Neptune, once seen as cold, lifeless orbs in the depths of space, were revealed to be dynamic, active planets with complex atmospheres and intriguing moons. These discoveries expanded our view of the solar system's outermost regions and underscored the importance of space exploration in uncovering the unknown. Now that we've explored the gas giants and ice giants, let's dive into the Voyager spacecraft's journey toward the edge of the solar system. Voyager 1's leap into interstellar space. The monumental moment when Voyager 1 crossed into interstellar space in 2012 marked not just the spacecraft's departure from the solar system, but the start of humanity's most ambitious venture into the unknown. It was a milestone decades in the making, and the data returned from Voyager 1 continues to offer groundbreaking insights about the region beyond the heliosphere. Once past the heliopause, the boundary where the solar wind loses its influence, Voyager 1 began to measure a dramatically different environment. The solar wind, which had previously buffered the spacecraft from the harsh radiation of interstellar space, faded away, making room for an increase in cosmic ray intensity. This transition opened up an entirely new field of study, allowing scientists to measure the effects of these high-energy particles, which had been hidden from Earth by the solar wind for most of human history. By analyzing the energy and origins of these cosmic rays, researchers now have a better understanding of the radiation environment that exists throughout our galaxy and beyond. Beyond cosmic rays, Voyager 1's journey through interstellar space revealed complex interactions between the solar wind and the interstellar medium. As it traversed this uncharted territory, the spacecraft encountered fluctuating magnetic fields, suggesting that interstellar space is far more turbulent than previously thought. This discovery is a key piece of the puzzle for understanding how stars interact with the interstellar medium, providing a glimpse into the galactic environment that shapes the evolution of galaxies. In this sense, Voyager 1's crossing represents more than a technical achievement. It is an unparalleled opportunity to study the broader forces that govern the cosmos. Voyager 2's journey continues. While Voyager 1 had already made its leap into interstellar space, Voyager 2's path took a longer, more methodical journey. This spacecraft, which began its voyage to Uranus and Neptune, now finds itself poised to follow in Voyager 1's footsteps. As it continues its journey beyond the solar system, the instruments on Voyager 2 provide a crucial comparison to the data returned by its twin. In 2018, Voyager 2 became the second human-made object to cross into interstellar space, completing a journey that had started nearly 4 decades earlier. Unlike Voyager 1, which had an immediate and dramatic shift when it crossed the heliopause, Voyager 2's passage was more gradual, giving scientists the opportunity to refine their understanding of this boundary and its effects on space phenomena. The differences in the crossing points between the two spacecraft have provided invaluable insights into the structure of the heliosphere and the way the solar wind interacts with the interstellar medium. In addition to the shared discoveries with Voyager 1, Voyager 2's proximity to the galactic plane presents an exciting opportunity for future studies. With different angles of approach, Voyager 2 may provide new observations of the interstellar magnetic field and cosmic rays, allowing for a more comprehensive picture of our solar system's transition into the vast expanse of interstellar space. The discoveries made by Voyager don't stop there. Let's look at how the spacecraft have helped reshape our view of the solar system's outer boundaries. New views of the heliosphere. Before the Voyager spacecraft made their groundbreaking discoveries, scientists had only speculative ideas about the outer boundaries of the solar system. The heliosphere, the bubble of charged particles created by the sun's solar wind, was thought to be spherical, expanding outward uniformly in all directions. However, the data collected by Voyager 1 and 2 as they crossed into interstellar space has forced scientists to reconsider this picture and instead has presented a much more complex view of our solar system's boundary. The most surprising revelation came from the shape of the heliosphere itself. Instead of the expected symmetrical spherical shape, scientists discovered that the heliosphere is squashed and irregular, likely due to the pressure of the interstellar wind. This wind, which comes from outside our solar system, is stronger on one side of the solar system than on the other. As a result, the heliosphere was found to be asymmetrical, with the solar wind pressing more on one side, causing it to compress and distort. The discovery of this irregular shape has provided valuable insights into how the sun's magnetic field interacts with the broader galactic environment. By studying how the heliosphere is influenced by interstellar pressure, scientists are gaining new insights into how solar systems interact with the interstellar medium. The reshaped view of the solar system's boundary has also led to more refined models of the solar system's place in the galaxy and how it fits into the broader galactic structure. What's more, these findings have implications beyond just our solar system. Understanding how the heliosphere interacts with the interstellar medium could provide key insights into how other stellar systems interact with the surrounding interstellar space. These discoveries are important not only for understanding our own solar system, but for understanding the conditions in other regions of the Milky Way galaxy as well. The Golden Record. In addition to its scientific instruments, each Voyager spacecraft carries a remarkable item, the Golden Record. This phonograph record, designed to be a time capsule, contains a variety of sounds and images from Earth, intended as a message to any extraterrestrial life that may encounter the spacecraft in the distant future. The Golden Record contains sounds from Earth, including greetings in 55 languages, music from various cultures, and even natural sounds such as birdsong, thunder, and the sound of the ocean. It also includes a series of images that represent life on Earth, including photographs of human beings, animals, landscapes, and scientific symbols. The inclusion of the Golden Record was a bold and optimistic gesture by NASA, aiming to communicate humanity's existence to potential extraterrestrial civilizations. While the chances of the record ever being discovered are slim, the Golden Record serves as a symbol of human curiosity, creativity, and the desire to reach out beyond our world to the stars. As Voyager 1 and 2 continue their journey into interstellar space, The golden record remains a testament to the spirit of exploration and the hope that one day our message will reach someone, somewhere beyond the stars. The ongoing journey. What's next for Voyager? Even as Voyager 1 and Voyager 2 venture farther into interstellar space, their journey is far from over. While the spacecraft are no longer within the range of Earth's direct control, they are still actively transmitting valuable data, offering glimpses into the mysterious realm beyond the solar system. The probe's power is gradually declining as their nuclear batteries lose energy, but engineers at NASA have worked tirelessly to keep these space explorers operational for as long as possible. Currently, it's expected that the spacecraft will continue to send data until at least 2030, if not longer, thanks to the advanced engineering that has kept them functional long past their expected lifespan. The ongoing journey of the Voyagers remains a profound testament to human ingenuity, determination, and curiosity. With each passing year, their transmissions offer new insights into the farthest reaches of our solar system and the first direct observations of the interstellar medium. As the spacecraft continue to drift further into the void, they are paving the way for future space exploration missions, helping to answer the many questions that remain about our place in the universe. But what lies ahead for the Voyager missions? While the spacecraft are moving farther away from us and the signals they send take longer to reach Earth, scientists are still eager to analyze their findings. One of the key questions that researchers hope to address in the coming years is how the interstellar magnetic field behaves. Voyager 1's data has already shown that this magnetic field is more complex and turbulent than anyone initially anticipated. Future studies of this data will continue to improve our understanding of how stellar winds interact with the interstellar medium and how those interactions affect the broader galactic environment. NASA is also working on future missions that will build on the groundwork laid by the Voyagers. The data collected by these two spacecrafts will likely serve as a stepping stone for upcoming missions that aim to explore deeper into the cosmos. In fact, new spacecraft are already being designed to study the boundary between the heliosphere and the interstellar medium in even more detail, learning from the lessons of Voyager's discoveries. While the Voyagers are far from home, they have set the stage for the next era of space exploration. The lessons learned from the Voyager missions will guide scientists as they plan new missions to explore more distant stars, planets, and even exoplanets outside of our solar system. Perhaps one day, another spacecraft will follow in Voyager's footsteps, venturing even further beyond the stars, continuing humanity's endless pursuit of knowledge. The legacy of Voyager. The Voyager missions have profoundly transformed our understanding of the universe. From their encounters with the gas giants to their journey into interstellar space, these spacecrafts have provided humanity with unprecedented insights into the outer solar system and beyond. Their discoveries have reshaped our knowledge of the solar system, the Milky Way, and the universe itself. One of the most significant impacts of the Voyager missions is their ability to push the boundaries of space exploration. Unlike many missions that focus on individual planets or moons, Voyager aimed to explore the cosmos beyond the solar system. By becoming the first human-made objects to leave the solar system, the Voyagers offered a new perspective on our place in the universe, sparking curiosity and inspiring future generations of explorers. Voyager's discoveries about the solar system's outer boundaries were groundbreaking. The spacecraft revealed that the heliosphere, a protective bubble of solar wind, has an irregular shape, influenced by the pressure of interstellar wind. They also detected cosmic rays and magnetic field anomalies, offering new insights into the environment beyond our solar system. The Voyagers also transformed our understanding of the planets and their moons. Voyager data revealed active volcanic activity on Jupiter's moon Io, a potential subsurface ocean on Europa, and the nitrogen-rich atmosphere of Saturn's moon Titan. These findings raised the possibility that some of these moons could support life, fueling further exploration. Culturally, the golden record included on both spacecraft serves as a message to potential extraterrestrial civilizations, symbolizing humanity's desire to connect with the universe. This gesture represents our curiosity and optimism about the future. The legacy of Voyager is far-reaching, continuing to influence space exploration. As Voyager 1 and 2 drift deeper into space, they remain a testament to humanity's insatiable curiosity and drive to explore the unknown. Their discoveries offer a sense of wonder and a blueprint for future exploration, inspiring us to look toward the stars. There you have it, the the incredible legacy of the Voyager missions. If you enjoyed this deep dive, don't forget to like, subscribe, and hit the bell for more space exploration content. Share your thoughts in the comments. What's next for space? Keep exploring, and we'll catch you in the next video.